this is not so easy to write on. This is the linearized pendulum equation. And sometimes when we get to higher order equations, we often get confused whether they're linear or not, but the definition of linear equation is that all terms are the first power of any derivative. That's called linear. So you will not have multiples of any two derivatives or any two theta terms, or multiples or powers. Also, both of these equations are second-order equations. By second order, we mean that the highest order of derivatives we take to is the second derivative. Okay, next we begin our discussion on homogeneous ODE. This is not only a homogeneous ODE, but it is a linear homogeneous ODE. Homogeneous means that this right-hand side of the equation is 0. Now my next question comes, what does 0 mean physically in our system? Okay, I have a quick answer this time. 0 means no inputs, so the U equals to 0. Very good. And if we want to correspond to a physical system, and the Y may be the actual measure that the measurement of the system. Again, this was our example that we showed for the first example, and then it has actual numbers for each coefficient. Next, let's look at how what kind of solutions we have for homogeneous linear systems. Linear systems can be of any order up to n, whatever order you claim it to be. You all know what this figure is. This is like a dash plot. Okay. Let's look at the next slide. So before we talk about solutions to ODEs, this is the most important function called the exponential functions. That is a main factor of our solution. What is the exponential function? It can be an expansion of this infinite series, or if you had high school here, I think you learned this equation in high school as the definition of E. And this one is another way to define exponential. I think someone blocked this. Oh, I'm sorry. This one, the function that is the solution here is the exponential function. And this definition is usually used in the calculus textbook. and you can prove from this to this and also to this. A very special property of this power series expansion is that it works for any real number t, which is not the case for any function. And of course, we should be familiar with the exponential function plotted. It increases fairly fast on the right-hand side, and it tends toward 0 in the negative side. So next, we see that we use the exponential function, exponential to some constant times t, as our guess solution. And it's quite reasonable guess because we know the derivative of exponential function itself is the exponential function. And if we plug this into the general linear homogeneous equation, we will get this polynomial of the coefficient gamma. For any polynomial of nth order, we can always decompose it into this form of n roots. And my question is that true? 所有的 n 次多项式都可以分解成这个形式，就是 r 乘上第一个根，r 减到第二个根乘上 r 减到第二个根 ，gamma minus the first root times gamma minus the second root times all the way to gamma minus the nth root. Is that always true for any nth order polynomial? Just yes or no question. If you think it's yes, raise your hands. If you think it's no, raise your hand. Okay. The answer is yes or no, depending on your condition. If you say it can be decomposed into the multiple of gamma minus gamma I, and gamma I can be real, complex, and then this is always possible. So